So much for coming in for today's class. Today we are going to be looking at a very brief topic, but very interesting and important. It's called the spanning tree concept, spanning tree protocol concept, and that is module 5 of our lectures. Now, we're going to be looking at it, and then we would be doing one demonstration of a spanning tree activity that we need to know. All right. Now, in this topic, we are going to be looking at the purpose of spanning tree protocol. Why do we need spanning tree protocol? What is the purpose? We're going to explain the common problems in a redundant layer 2 switch network. We're also going to look at the spanning tree protocol operations and explain basically how STP operates in a simple switch network. We are also going to be looking at the evolution of spanning tree protocol and explain the concept of rapid Per-VLAN spanning tree protocol and how it operates. All right, so let's go straight. Now, what is the purpose of spanning tree protocol? The main aim of spanning tree protocol is when you build a network with redundancy, you want to avoid certain loops, certain looping of certain kind of traffic. So this topic basically covers this kind of loops that takes place at the layer 2 of the OSI model and explains how this protocol actually works, especially when we have a lot of redundancy in our network. Because redundancy is very, very important, okay? Especially when you have disruption of network and you want to prevent that. So you need redundancy. So spanning tree protocol is just the set of rules that governs how you can have redundancy on your network and yet you will not have loops, or yet you'll be able to prevent loops that takes place in your network. Now, like we said, spanning tree is a loop prevention protocol that allows us to create so much redundancy on our network, and it logically blocks any physical loops in the network. So if you look at this diagram, for instance, I have network for PC 1, 2, 3, and PC 4. And I have a network design for 3 switches, switch 1, switch 2, and switch 3. Now, these 3 switches are connected to each other. All right, switch 1 is connected to switch 2, switch 2 is connected to switch 3, switch 3 is connected to back to switch 1. And the funny thing you need to know is that they are all within the same broadcast domain. Okay, these switches that are connected are within the same broadcast domain, and as such, there is going to be a loop, because if I send a particular, if this guy sends a particular message that is not destined to any of these pieces, it comes here and it comes here. The one coming here goes here, and this one comes, so it continues, and it chokes the bandwidth of your network, it slows down your traffic, and there are a lot of hazards that it can cause. All right, so basically spanning tree is a way to look at this kind of scenario, calculate which port that logically needs to be blocked so that it's going to avoid these loops. So basically that's what spanning tree does. So path redundancy provides multiple network services by eliminating the possibility of a single point of failure. So when multiple paths exist between 2 devices on a network, and there is no spanning tree implication on the switches, a layer 2 loop occurs. A layer 2 loop can result in MAC address table instability, all right, link saturation, and high CPU utilization on switches and devices. And that is going to result in your network becoming very, very unusable. All right, so layer 2 Ethernet does not include a mechanism to recognize and eliminate this endless loop of frames that continues to go round and round and round. But both IP version 4 and IP version 6 includes a mechanism that limits the number of times a layer 3 networking device like a router can transmit a particular packet. So a router can decrement the TTL value. TTL simply means time to live in every IP version 4 packet. Now, what are we talking about TTL? Let me show you, for instance, if I come to my command prompt, let me launch my command prompt, then share it with you so that you will now see what I'm talking about. Let me share it with you. Okay, so I believe you can see this. Now, if in this my command prompt, I decide to send a ping to, let's say, Google, for instance, and I type ping google.com and I press enter, I am going to get a reply. Now, this ping is just an end-to-end network troubleshooting tool to verify the availability of a remote device. Okay, now, when you get this reply, it simply means that your my host system sends a message to check the availability of a particular remote device and has come back with a response to give me. And this is the response: a reply from 216.58223.238. And then it's telling me the size of the reply. It's telling me how long it takes. Now, there is a value called TTL here. This TTL is basically like time to live. Time for what to live? It is time for this packet to live. It's like I am sending somebody on an errand and I am saying, okay, I am going to give you 5 minutes to go and deliver this message and come back. And within this particular period, if you are unable to come back, I will declare you unreachable, whatever happens on the way or so. So I'm going to give a time that this particular message is going to be. If not, it's going to be declared invalid. So I send a particular ping and I expect to get a response. All right, the response either unreachable or whatever. But the moment that the time expires, then you will get a message such like request timed out. So what we are saying here is that a layer 3 that uses both IP version 4 and version 6 includes a mechanism that have to limit the number of times this particular packet can be retransmitted over the network. This is basically to avoid this loop. So the hop limit field in every IP version 4 packet and IP version 6 exists where this particular value is stated. So when these fields are decremented to 0, the router will drop the packet. Ethernet and Ethernet switches have no comparable mechanisms for limiting the number of times a switch retransmits a layer 2 frame. STP was developed specifically as a loop prevention mechanism for layer 2 Ethernet. All right. So when you have a switch network and you're going to have a lot of redundancy, it is very, very important that you understand the concept of spanning tree so that you do not have consistent and persistent looping that continues to occur on your network. So without STP enabled on your network, layer 2 can loop so many times and it will cause a lot of broadcast, all right, and multicast, and it will cause a storm on your network. And this can bring down your network very, very quickly. All right. So when a loop occurs, the MAC address table on that switch would constantly change with the update from the broadcast frames, which results in MAC address database instability. And remember, your switch does its forwarding based on the information that is in its MAC address table. Okay, that's what it used to make its decision. So an unknown unicast frame is when the switch does not have the destination MAC address in its MAC address table and must forward the frame out through all ports except the one it came in. So we are saying that if in my switch I am supposed to have a particular what do we call it now? A particular port that governs how traffic moves out of my network and into my network. For instance, I have a switch that connects multiple devices. So in that particular switch, there's a MAC address table. Within that MAC address table, it has the details of every end device that is connected to that particular switch. So if a friend comes and is supposed to go to a particular destination, it checks the table for the corresponding port number and then just forwards that particular frame through that particular port number. And that's how it makes its decision. Okay, but once this particular instability in database begins, MAC address table begins to occur, what we are saying here is that the MAC addresses that are mapped to the different ports are going to be changing. They're going to be changing. So there might be a particular frame that is required to go to a particular destination device. Now, if the MAC address of that particular destination device is not within the MAC address table of that switch, the switch will forward it through all the ports that are in its that are on the switch. If it is a 24-port switch, it's going to forward to 23 ports. Why 23? Because it's going to exempt the port that the frame came through. Okay, so basically we are calling that kind of scenario a broadcast storm. All right, so a broadcast storm is an abnormally high number of broadcasts overwhelming the network during a specific amount of time. So broadcast storms can disable a network within seconds by overwhelming the switches and the end devices. So broadcast storm can be caused by hardware problems such as faulty network interface cards or maybe a layer 2 loop that is going to be happening over and over, especially when you have multiple of these particular switches that we're talking about. So a layer 2 broadcast in a network such as address resolution protocol requests are very common, all right? And a host caught in a layer 2 loop is not accessible to other hosts on that same network. Additionally, due to the constant changes in the MAC address table, the switch does not know out of which port to forward the unicast frame. And that's just what I explained. So in order to prevent this kind of issues from occurring, all right, in redundant networks, some type of spanning tree protocol must be enabled on the switch so that the switch will be able to calculate and determine where all this loop is coming up from and decide to block it. So if spanning tree is enabled on the switch, so by default, the Cisco switch will prevent it because automatically by default it is enabled unless you want to stop it. So now, what is then the algorithm that does this calculation? Because we are saying that it will have to calculate the, how would I put it, the loop that is going on and the ports that are associated with this loop and decide which port is going to be blocked because it is the redundant, which port is going to be blocked. So if the switch does this calculation and blocks the port, then the loop is stopped. Okay, so what metric is it using for this calculation? That's the algorithm we're talking about. So STP is based on an algorithm invented by Radia Palmer while working for Digital Equipment Corporation and published since 1985. All right. An algorithm for distributed computation of a spanning tree in an extended local area network. So a spanning tree algorithm creates a loop-free topology by selecting a single root bridge where all other switches determine a single least cost path. All right? All the switches determine the single least. So the root bridge is just a port that is tagged the root bridge. All right? And we're going to know more about the root bridge. So the STP prevents loop from occurring by configuring a loop-free path through the network using strategically placed blocking state ports. So if the switch determines that there is a loop on the network, it's going to pick one of the ports and call it a root bridge. Then it will pick one and call it designated. Then it will pick one and put it in the blocking state. All right? The one that is in the blocking state means that frames will not be forwarded through that particular port. So the switch running STPs are able to compensate for the failure by dynamically unblocking the previously blocked port and permitting traffic to traverse the alternate path. All right, that is helping the concept of the redundancy to actually work. So how does the switch now select the root bridge? Okay, how does it select and know, okay, this port should be the root bridge? How does it do that? So selecting the root bridge, the bridge is the reference point for the entire network to build a spanning tree around. So block redundant paths. The STP ensures that there is only one logical path between all destinations on the network by intentionally blocking redundant paths that could cause the loop. So when a port is blocked, user data is prevented from entering or leaving that particular port. So create a loop-free topology. What happens to that? A block port has the effect of making that link non-forwardable link between the two switches. This creates a topology where each switch has only a single path to the root bridge, similar to branches on the tree that connect to the root of the tree. So how does it recalculate the link failure? The physical paths still exist to provide redundancy, but these paths are disabled to prevent the loop from occurring. If the path is ever needed to compensate for a network cable or switch failure, STP recalculates the path and unblocks the necessary port to allow the redundant paths to become active. So STP calculations can occur many times in a new switch, or new inter-switch link is added to the network. So what we are saying is that basically, if I have 2 switches or 3 switches or 4 switches, and each of these switches are connected to each other, there is a tendency that there is going to be a loop, because the frame is going to keep going round and round and round from one port to the other, from one port to the other, and that can cause us that can cause us problem that we are talking about. So the best case scenario is for this STP to come on place, and once it comes in place, what it does is that it selects the port that generates the loop and block it, so that your traffic would be able to flow. So how does it operate? First, it elects what we call the root bridge, and it does its election within itself, even though you can actually read that election, but it does the election, and then it elects the root bridge, which is the switch. You select which switch amongst the 3 switch, which switch is going to be the root bridge, or the root switch rather. Then it's going to elect the root port. Okay, so apart from the root bridge, which is the root switch, then it's going to select the root port. Okay, then it's going to elect the designated port, and then it's going to now elect the alternate port. All right, so during the STA and STP functions, switches use bridge protocol data unit. We call it BPDU. Excuse me, BPDU, Bridge Protocol Data Unit, to share information about themselves and their connections. So BPDU are used to elect the root bridge. Now, this is like a communication that happens between the switches themselves. Switch 1, switch 2, switch 3, they are talking amongst themselves. So they will say, who amongst us is going to now be our root bridge? And then they elect the device. All right. So, and they share this information automatically amongst themselves using the BPDU. All right. Now, each BPDU contains the bridge ID. We call it the BID. All right. That identifies which switch sent the BPDU. All right. Now, we are saying, instead of everybody sending information to everybody, switch 1 is sending to switch 2, switch 2 is sending to switch 3, switch 3 is sending to switch 4, and continuously like that. They are trying to get organized to say, okay, we are 3 of us, 3 switches here, or we are 10 switches here, or whatever it is we have. Why don't we elect one switch where all of us will be sending our information to that particular switch? So instead of us to select, instead of us to allow everybody to be sending to everybody, let's select one particular switch. We call it the root bridge, where every other switch will send its information to that particular switch. That's the concept. And how it sends this information is called the bridge protocol data unit. All right, it's just a protocol that governs how this information are sent. Now, the bridge ID, all right, is basically like the MAC address of that particular switch or that particular bridge, all right, or of that particular port. We're going to look at that very soon. So the BID contains a priority value, the priority value, the MAC address of the switch, and an extended system ID. The lowest BID value is determined by the combination of these three fields. So let's look at it. What are we talking about? We're trying to find out, okay, since every switch has a bridge ID, what is it that makes up this bridge ID? Okay, what is it that makes up this bridge ID? We said the MAC address is part of it. All right, and then we have a particular value that is added to that particular MAC address that helps in that particular identification of that BID. So we're going to find out how it does that. Now, the default priority value for all Cisco switches is the decimal value 32768. So the range is 0 to 61440 in increment of 4096. A lower bridge priority is preferable. The bridge priority of 0 takes precedence over all other bridge priorities. Remember that you have the bridge ID as the MAC address of the bridge and the priority value. Okay, and we are saying that this priority value ranges from what? From 0 to 61440. Okay, and we are saying that the switch is going to assume any of these values unless you decide to assign it. You can assign a priority value to a particular switch. But if you do not assign, by default, the switch will take on a priority value of 32768. Okay, it will take that as a priority value. So if I have 3 switches, that means each of them will have the same priority value of 32768 in addition to their MAC address. So the switch now is going to now recalculate, or is going to now calculate the size of the MAC address. And based on the size of the MAC address, the one with the lower value is the one that is going to be elected as the root bridge. But if you don't want that to be, then you have to now manually assign the priority value so that you can determine the root bridge. Now, the extended system ID. The extended system ID value is the decimal value added to the bridge priority value in the BID to identify the VLAN for this bridge protocol data unit. When 2 switches are configured with the same priority, they have the same extended system ID. The switch having the MAC address with the lowest value expressed in the hexadecimal will have the lower BID. So we are looking at 3 components that makes up the BID. Okay, that's the bridge priority, the extended system ID, and that has to do with the VLAN. That has to do with the VLAN. Then you have the MAC address. Okay. Now, the STA designates a single switch as the root bridge. We have this switch. This is switch 1. It has a priority of 24577, and this as the MAC address. This is switch 2. It has a priority of 32769, and this is the MAC address. This is switch 3. It has a priority of 32769, and this is the MAC address. Now, how is this guy now the root bridge? Because the value of the priority 2457 is the lowest compared to the priority values of these 2, irrespective of the size of their MAC addresses. Okay, so all switches in the broadcast storm participate in the election process. After a switch boots, it begins to send these bridge protocol data unit frames every 2 seconds. This bridge protocol frames contains the BID of the sending switch and the BID of the root bridge, known as the root ID. So the switch with the lowest BID will become the root bridge. At first, all switches declare themselves at root bridge with their own BID set as the root ID. Eventually, the switches will learn through the exchange of bridge protocol data units which switch has the lowest BID and will agree to be the root bridge. So, because of the default value of 32768, which is the default BID for all Cisco switches, it is possible for 2 or more switches to have the same priority in this scenario. So where the priorities are the same, the switch with the lowest MAC address will become the root bridge. The administrator should configure the desired root bridge switch with a lower priority. And when you do that, it helps the switch to be able to determine who is the root bridge. Okay? It helps the switch to make this particular decision. But importantly, we need to know that every switch comes with a default value as I am the root bridge. I am the root bridge. That's what every switch is going to tell itself until this exchange of information begins to take place. Okay? So that is the point we are making. Note, the priority of all the switches is 32769. The value is based on the 32768 plus the value of the VLAN. The default VLAN for all switches is 1. That's VLAN 1. So it will take, remember we looked at three items. We have the priority value, we have the VLAN ID, and then you have the MAC address. Okay, but it looks at it in that order. So if every switch has a default VLAN of VLAN 1 and has a default priority value of 32768, you now add the 1 plus 32768, it will give you 32769. As like what we see here, this particular switch has VLAN 1 and has a priority of 32768, the same as this particular switch. So I, as the administrator, if I prefer this switch to become the root bridge, all I just need to do is log into the switch and change the priority number or the priority value. If I do that, then I'm okay. Now, we have looked at the root bridge. So when the root bridge has been elected for a given spanning tree instance, the STA starts determining the best path to forward the root bridge from all destinations. So in the broadcast domain, the path information known as the internal root port, path cost is determined by the sum of the individual port cost along the path. All right. So I am taking a journey to a particular destination. So I begin to look at how many ports do I need to meet before I get there, and what is the bandwidth for each of these ports. All right. So I put all these values into consideration so that I can be able to make my decision. So when a switch receives the PBDU, it adds the ingress port cost of the segment to determine its internal root path cost. The default port costs are determined by the speed at which each of the ports operates. So whether it is a whether it's an Ethernet port, or it's a fast Ethernet port, or it's a gigabit Ethernet port, whatever port it is, the speed actually plays a very, very key role in it. And so it's important that we know that. All right. So the default port costs are defined by the speed at which the port operates. So the table, actually, we have this table that you see here actually shows the default port cost suggested by the IEEE. So Cisco switches by default use Cisco ports by default use the values as defined in the IEEE 82.1d standard. All right, so this is what it shows, that if I have a port that is 10 Mbps, if I have a port that is 10 Mbps, this is the value that I attach to it. All right, because I have, okay, let me put it to, although switch ports have a default port cost associated with them, the port cost is configurable. The ability to configure individual port costs gives the administrator the flexibility to manually control the spanning tree paths to the root bridge. Remember, we're looking for the root port. All right, and the STP cost for 10 Mbps is 100, which means that is the least preferred. The STP cost for a fast Ethernet, which is 19, which is more preferable than this. Why? Because this is a higher bandwidth. The cost for 1 gig port is 4, and the cost for 10 gigabit ports is 2. So by default, this is the cost that is assigned to the ports. All right, and then the one for RSTP for 10 Mbps is 2 million. For 100 Mbps, that is fast Ethernet, is 200,000. For 1 gigabit is 20,000, and for 10 gigabit is 2,000. All right, so we have here that after the root bridge has been determined, the ST algorithm is used to elect the root port. Every non-root switch will elect one root port. Okay, so if I have 3 switches, as you can see on this diagram, this is my root bridge. My root bridge is the root switch. So within the root bridge, I don't need to elect a root port. Okay, but every other switch that is not a root bridge is going to have a root port. Okay, that's the point we are saying. So the internal root cost is equal to the sum of all the port costs along the path to the root bridge. All right, like we see here. For instance, look at this. We have path 1, we have path 2, we have path 2 here. Switch 1 and switch 2 are, you are having path 1 that is going here. Path 1, the cost is 19 times 1, which is 19. All right. One of the path 2 costs here, this path 2 cost, if this traffic is coming to this place and is coming to this here. So it's going to now say the cost is 19 times 2. Why am I multiplying it by 2? Because the traffic will come to this switch and then it will now come to this switch. So I am multiplying it by 2. All right. So the switch will do this calculation of this distance. Then it will now determine, I would prefer this port to be my root port. Remember, the root port is there to determine which port is going to be forwarding the messages to the root bridge. Okay, so the root port is the guy that determines how to do that. So this particular switch also has a root port, and this is the root port here. All right, because it's the distance that is going to calculate from itself to the root bridge. All right, so if it calculates the distance, then it's going to determine who becomes the root port. All right, now how about designated ports? Every segment between 2 switches will have one designated port. The designated port is a port on the segment that has the internal root path cost to the root bridge. In other words, the designated port has the best path to receive traffic leading to the root bridge. What is not the root port or the designated port becomes the alternate or block port. For instance, I have the root bridge here, and in this root bridge, all the ports are designated. All right, all the ports are designated from the root bridge. All right, this port here is designated, this is designated, this is designated. Now, if I come to switch 2, this one is already determined as my root port. Definitely, the next one connected to the next switch is what? Is designated. Then this one I have here, I have a root port. So by default, ordinarily, I would say the next one is going to be designated. But look at it, it has not been labeled as designated. If it is labeled as designated, then definitely I am going to have a loop on this network. So definitely this guy is going to be the alternate port, or is going to be in the blocking state. Why? Because already this switch 2 has determined that I am going to be forwarding my packet to the my frame to switch 1 through this particular port. This is my root port. And then switch 3 is said I'm going to be forwarding my own through this port. This is the root port. So who then uses this link? No one. So if we allow this link to flow, then we're going to have a loop. So the best case scenario is now to block the link. And that is what spanning tree is going to now do. So after determining the root bridge, and what does it use to determine the root bridge? It uses the priority value, it uses the VLAN number, and then it uses the MAC address. These three elements, all right? Once it determines it, all the ports within that particular root bridge becomes designated ports. Designated ports are ports that receives that forward packet to the root bridge. All right. So any other port, any other switch on the network is going to now calculate the path closest to the root bridge, and that particular port becomes its root port. Okay, it becomes its root port. Any other port is designated except the one that is going to be blocked to serve as a redundant port. So when a switch has multiple equal paths to a root bridge, the switch will determine a port using the lowest criteria, the lowest BID, the lowest sender port priority, and the lowest sender port ID. So you see, in this particular case, we did the calculation from this switch. This is shorter than this distance. So, but in a situation where the distance is the same, look at this scenario, for instance. Okay, look at this scenario for distance. You have, you have a root bridge here as switch 1. Now, this root bridge that is here, every port is a designated port. So I have a designated port here, I have a designated port. In this particular switch 4, this is my root bridge. In switch 2, this is my root bridge. In switch 3, this is my root bridge. So I'm going to block this. But we're looking at a situation where you have the same distance. For instance, switch 2. Switch 2 is going to have the same distance to get to switch 1. If it follows this link here, it's going to have the same distance as when it follows this link here to the same distance. So the topology has 4 switches with switch 1 as the root bridge. Port 01 on switch 3, which is this guy here, port 01 here, and port 03 on switch 4. This is switch 4. Port 01 here and this port here have been selected as root ports because they have the root path cost to the root bridge for their respective switches. But switch 2 has 2 ports, that is port 02 and port 01, with equal cost to the bridge. All right, the bridge ID of switch 3 and 4 will be used to break the tie. The bridge ID for this guy here, look at the bridge ID here, and the bridge ID for this guy here, this is the ID here. So who has the lower bridge ID? That is switch 4. All right, switch 4 has the lower bridge ID. All right, so the bridge ID of switch 3 and 4 will be used to break the tie. This is known as the sender BID. Switch 3 has sent this as its BID, and switch 4 sends this. So because switch 4 has a lower bridge ID, this guy here, this switch is going to now forward its frame through this particular port. All right, so that's just how it breaks the tie. Now, this topology you see here has 2 switches which are connected with 2 equal cost paths between switch 1 and the root bridge. Look at it. I have 2 switches here, switch 1 and switch 4, and they are all connected to each other. This is the BID here, this is the BID here. This guy has been selected as the root bridge because it has a lower BID. That's why it's been selected as the root bridge. So all its ports are designated. All right. So what does it mean? Does it mean that we're going to have a loop? Yes, we're going to have a loop unless something is done. All right, unless something is done. So switch 4, which is this guy here, has 2 ports with equal cost to the root bridge. Because both ports are connected to the same switch, the sender BID S1 is equal. So the first step is a tie. The next is the sender switch 1 port priority, which is this guy. The default port value of 128. So both ports on switch 1 have the same port priority. There's also a tie. However, if either port on switch 1 was configured with a lower port priority, would put the adjacent port in a forwarding state. The other port would be on the blocking state. All right. So since you see you have these two, if you want to, you have to now change the value of one of the ports here. All right. If you configure the priority value of one of these lower, then you would have solved your problem. So the last tiebreaker is the lowest sender's port ID, which switch 4 has received its PPDU from this guy here. All right, F01. And then it will automatically now use this guy as the alternative, and then it will not block it. So the decision is based on the sender port ID, not the receiver's port ID, because the port ID of switch of F01 on switch 1 is lower than the port ID. So this is port ID of 0/1 is lower than 0/2, which is lower than 0/3, which is lower than 0/4, and things like that. So 0, 1, 2, 3. So those are the port IDs we are talking about. So the switch is now going to now use the sender's port ID to determine which guy is going to take the day. Now, the STP convergence requires 3 timers. All right, we have the hello timer, we have the forward delay timer, and we have the max age timer. Now, let's look at each of these timers. The hello timer is the interval between the BPDUs. That means each time the switch sends its message, its information to the next switch, that is, it sends a hello. All right, and the hello is just those bridge protocol data units, those BPDU. All right, so the time frame between the first and the second is the hello time. All right, then the forward delay timer. The forward delay timer is the time that is spent in the listening and learning states. The default is 15 seconds. The default for the hello timer can be modified. The default is 2 seconds, but it can be modified between 1 and 10 seconds. But the default is 2 seconds. But the delay timer is 15 seconds, and it is the time spent in the listening and learning stage. Then the age timer, the max age timer, is the maximum length of time that a switch waits before attempting to change the STP topology, which is true. So before it recalculates, it has to exhaust its age timer. All right, and the default is 20 seconds, even though you can adjust it between 6 and 40 seconds, but the default is 20 seconds. All right, so STP facilitates the logical loop-free path throughout the broadcast domain. The spanning tree is determined through the information learned by the exchange of the BPDU frames between the interconnected switches. If a switch port transitions directly from blocking state to forwarding state without information about the full topology during the transition, the port can temporarily create a data loop. For this reason, the STP has 5 port states, for which four of which are operational ports, as we can see here. We have the blocking state, we have the listening state, we have the learning state, and we have the forwarding state. Blocking, listening, learning, and forwarding. Now look at the port states here. So the port is, once a port in its blocking state, it can only receive PBD. All right, but no updates. One is in its listening state, it can receive PBDUs and send PBDUs, but no updates. One is in its learning state, it can receive and send PBDUs and even update the table, the MAC address table. All right, once it is in its forwarding state, it can receive and send, it can update table, and it can forward data frames. But once it is disabled, it cannot receive nor send, and no updates at all. All right. Now let's look at Per-VLAN spanning tree. Spanning tree can be configured to operate in an environment with multiple VLANs. In Per-VLAN spanning tree versions of STP, there is a root bridge elected for each spanning tree instance. This makes it possible to have different root bridges for different sets of VLANs. STP operates a separate instance of STPs for individual VLANs. In all ports on all switches are all members of VLAN 1. Then there is only one spanning tree instance. What we are saying is that if I have a switch that have multiple VLANs, I can create Per-VLAN spanning tree. So on a particular switch, instead of having a root bridge, the root bridge is going to now be logical. Okay, it's going to be logical. Now let's look at the evolution. The evolution basically describes the different types of STPs that we have and the versions. All right, so many professionals generally use spanning tree and STP to refer to various implications of spanning trees, such as rapid spanning tree and multiple spanning tree protocols. In order to communicate spanning tree concepts correctly, it is important to refer to the implementation or standard of spanning tree in context. So the latest IEEE documentation on spanning tree, STP says STP has now been superseded by rapid spanning tree protocol. That is, it uses STP to refer to the original implementation of the spanning tree and RSTP to describe the versions of spanning tree specified. Because the two protocols share much of the same terminology and methods for the loop-free path, the primary focus will be on the current standard and Cisco proprietary implications of STP and RSTP. Cisco switches running iOS 15 or later run Per-VLAN spanning tree by default. This version incorporates many of the specifications of IEEE, all right, such as alternate ports in place of former non-designated ports. Switches must be explicitly configured for rapid spanning tree mode in order to run the rapid spanning tree protocol. So these are the different versions that we have. We have STP, Per-VLAN spanning tree plus, rapid Per-VLAN spanning tree prop, then rapid Per-VLAN spanning tree plus. We have multiple spanning tree protocol and multiple spanning tree. Now let's look at each. STP is the original 802.1 that provides a loop-free topology in a network with redundant links. Okay. Now Per-VLAN spanning tree plus is a Cisco enhancement of STP that provides a separate spanning tree instance for each VLAN. Okay. Then 802.1d is the update version of STP. Now, RSTP is rapid spanning tree protocol. All right, and it's an evolution of STP that provides a faster convergence of STP. So RSTP is has faster convergence of STP. Then we have rapid Per-VLAN spanning tree plus. So we have rapid PVST here. All right, this is also an enhancement of rapid spanning tree protocol that uses per-VLAN spanning tree provides separate instance of 822.1w per-VLAN. All right. Then we have multiple spanning tree protocol, like we discussed earlier. It's a Cisco proprietary. All right, and it maps multiple VLANs into the same spanning tree instance. Then multiple spanning tree is the Cisco implementation of multiple spanning tree protocol, which gives up to 16 instances of RSTP and combines many VLAN with the same physical and logical topology into a common RSTP. Okay? So these are the concepts that we are looking at based on what we have. The port states, there are only 3 port states in rapid spanning tree protocol that corresponds to the 3 possible. All right, look at it that we have. This is the spanning tree. We said we had 4. We have forwarding, listening, forwarding, learning, listening, blocking, and then disable, the 5. But in rapid spanning tree protocol, we are having what? Learning, forwarding, and discarding. Discarding comprises of disabled, blocking, and listening. All right. So this is what we're talking about. The alternate port has an alternate path to the root bridge. The backup port is a backup to the shared medium, such as a hub. A backup hub is less common because hubs are now considered legacy devices. So I have my root bridge, I have my switch 2 and switch 3 here. So to avoid loop, I block this and then I block this as backup. But if for any reason this particular link fails, or this one, then this guy is going to be unblocked so that this guy will be able to send to switch 1. All right. So we're talking about the evolution. So when a device is connected to a switch port, or when a switch powers on, the switch port goes through both the listening and learning states, each time waiting for the forwarded delay timer to expire. This delay is 50 seconds for each state for a total of 30 seconds. This can present a problem for DHCP. So when a switch port is configured with port fast, you can enter the switch and tell it pause fast. That port transitions from blocking to forwarding state immediately, avoiding the 30 seconds delay. You can use port fast to access ports to allow devices connect to these ports to access the network immediately. Port fast should only be used on access ports. If you enable port fast on a port connecting another switch, you risk creating a spanning loop. A port fast enabled switch port should never receive PBGUs, because that would indicate that the switch is configured to the port, potentially causing spanning tree loops. So Cisco switches supports a feature called the BPDU guard. When enabled, it immediately puts the switch port on an error disabled state upon receipt of any BPDU. This actually protects it against potential loops by effectively shutting down that particular port. The alternatives to STP, depending on the implementation, layer 2 may include not only the access layer, but also the distribution or even the core layers. These designs may include hundreds of switches, which 100 over even thousands, or even thousands of VLANs. STP can adapt to the added redundancy and complexity with enhancement as part of RSTP and MS RSTP. All right. So this is very important. Layer 3 routing allows for what? Redundant paths and loop in the topology without blocking ports. For this reason, some environments are transitioning from layer 3 everywhere except where devices connect to the other layer switch. In other words, the connections between access layer switches and distribution layer switches will be layer 3 instead of layer 2. Now, ladies and gentlemen, the concept we have looked at today basically is a way to prevent loop in a network, in a switch network with redundant links. Okay, you have redundant links in your network, and you want to prevent loops on your network. Spanning tree is the protocol to use, and we have seen that you can have different of these spanning trees. You can have the Per-VLAN spanning tree. You can have the rapid Per-VLAN spanning tree. And in fact, let's even look at a particular packet tracer. Let me share it. Let's just do that briefly. Okay. So look at this packet tracer activity. I encourage you to do, but it's just a demonstration so that you will understand the concept of spanning tree. Now, look at this loop here, this topology here. I have switch 1, switch 2, and switch 3. Now, if you observe, one of these particular ports is amber. All right, it's in its blocking state. But let's follow the activities and see what we have. There's this activity. In this activity, you use packet tracer to observe the operations of spanning tree protocol in a simple switch network that has a redundant path. All right, so we should ping from PC1 to PC2. PC2 is 192.168.1.101. So let me ping that. So, come on. So, ping 192.168.1.101. All right, so my ping is successful when I am pinging from PC1 to PC2. The question is, which path do you think my traffic is going through? All right, is it coming through here or is it coming through here? Let's run the ping again on simulation mode. Let me see. All right, so let's run the ping again. Run the ping, and then let's see where it goes. So you see, this is the ping. All right, this is from PC1. Let's see how it moves. If I come, you see, it comes to switch 1. All right, from switch 1, that is from PC1, it comes to switch 1. Then where does it go? It goes to switch 2. All right, then from switch 2, where does it go? It goes to PC2. All right, then we're expected to get a reply. The reply goes from PC2, and then it goes to switch 2, then comes to switch 1, and then comes to PC1, and that ends. Okay, so you see, that ends. So the point we are making is that if you observe, the traffic did not come through switch 3. It didn't come here. It has nothing to do with this guy. Why? Because the spanning tree has blocked this particular port. All right. So it says use the show spanning tree VLAN 1 command to gather information about the spanning tree on each of these switches. So let me come to switch 1, for instance. All right. All right. Enabled. So show. What command did they say? Show spanning tree VLAN 1. Okay, show spanning tree VLAN 1. Now, if you look at this command on switch 1, what does it tell us? That we have 3 ports that we are using here. Out of these 3 ports, one of it is the root port. Which one is the root port? We are on switch 1. The root port is gigabit 02, which is this guy. This is the root port. And if this is the root port, it definitely means that this guy is not the root bridge. Probably this guy is the root bridge. Okay? Switch 2 is the root bridge, possibly. Because the root port points to where the root bridge is. All right, so here we have the root port as gigabit 02 as root port. Then we have this guy and this guy as designated. All right, so let's go to the next switch. Let's come to this switch, and then let's run show spanning tree VLAN 1, and let's see what we have. Okay, here we have two ports that are being active, G01 and G02. And look at it, G01 and 02. Look at it, one is the root port. So you see this guy, one is the root port, and then two is the alternative port and is on the blocking state. So you see this guy is being blocked. So if this guy is the root port forwarding here, this guy is the root port forwarding here, definitely this guy is the root bridge. So let's verify. How do we know it is the root bridge? Let's come and run the same command, and then show spanning tree VLAN 1. Okay, because we are running a Per-VLAN spanning tree. Now look at it. All these ports, there is nothing like the root port. Can you see? All of them are what? Designated ports. So because there is no root port, all of them are designated. Definitely this guy is the root bridge, because all the other ones are pointing to it. So they are all designated. Can you see? All right. So they said we should fill in this particular information, of which we have just done. All right. That we should remove the connection between switch 1 and switch 2. Okay. So if we remove this connection, what does it mean? It means that this guy is going to unblock. All right. So let's come in here. Let's remove. Where's the delete for? Where's the delete? Where's the delete tool? I've forgotten where this delete tool is. Okay, so I've deleted it. All right, so if we're taking off this particular link, what do you think will happen? This guy is going to recalculate, these switches are going to recalculate, and once they recalculate, they send each other BPDUs, then this guy will turn green. So we have removed, where is it? Remove the connection. Okay, we have removed. So show spanning tree. So we're going to now run the ping and see. Uh-oh, what did I do? What did I do? What did I do? Let me undo. All right. Okay. So let's run our ping again. All right. Aha! Now look at it. It is green now. All right. Let's run our ping. What are we pinging? We're pinging 192.168.1.101. Ping. Let's put it on simulation mode. Ping 192.168.1.101. Okay. All right. So you see that there is no blocking state. This guy receives the message, the frame is going to forward it here, and once he forwards it here, you will forward to this guy, and then you forward to switch 3, and then it will get to switch 2 to PC2. Then from PC2, it will now begin to send the reply. Okay, you send the reply, and then to switch 2, then to switch 3, then to switch 1, then to PC1, Very good. And then we're good. So now if I enter this switch then, and then I run the same command. Now see what we've got. We have the root bridge as what? G0/1, which is this guy. The root port, sorry. This port here is G0/1. Initially, what did we get? Look at it. Our root port was G0/2 initially. But now, our root port now has changed to G0/1. If we come to switch 3, for instance, and we run the same command, let's see the differences. You see, G0/1 is still the root port, but G0/2 has become the designated port. What was it before? Before it was an alternate port. Can you see? Before it was an alternate port, but now it is a designated port. Okay? And then if we come to this, rerun the command, all right, we still have our designated port. So we don't have the third one. So you see, the point we are making here is that just by the removal of this link between here and here, we've gotten. So if we pick the link and we decide to connect G0/2 to G01, all right, the switch is going to now do its recalculation. Once it does its recalculation, then you will see that the information is going to change. So while the ports are initializing, let's wait for them to turn green. Let's run our thing and wait for it to turn green. It's timing out because none of the ports you see here is amber. This guy is also amber. All right, so we have a reply now. All right, so in real time, what do we have? Okay, sorry, let me run the command again. Okay. Simulation mode. All right, so you see, because I'm coming here, this guy is in blocking state, so the message will come here, and you see, and then it will come here. It will avoid this guy. So it is the spanning tree that is able to block it, just to make sure that there is no loop on it. Okay. So basically that is this activity, and I think that is what we have on spanning tree. It's a very interesting protocol, and we highly encourage it for you to run it on your campus network or any switch network that you have to avoid loops. And you can do some practice. You can do some practice on it, and I hope to see you guys on Thursday when we meet next. Thank you so much for paying attention in today's class. I hope we have all gotten something. All right. Thank you very much. So we see you on Thursday. But before I forget, just don't forget you have